Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
All right, welcome to The Explainer. This is week 10, part 2. So you've definitely seen it all over the place. AI that can take a few words of text and whip up a mind-blowing image. It feels like actual magic, right? Well, today we're going to pull back the curtain on the incredible science that makes it all happen. It's a process called the diffusion model, and we're going to see how it all starts with nothing but random noise and ends up with a masterpiece. Let's dive in. So this really gets to the heart of the problem. I mean, taking a perfectly good picture and just drowning it in noise until it's a fuzzy mess of static, that's the easy part. Anyone can do that. But going backwards, starting with pure randomness and somehow pulling a perfect image out of it, that's the real trick. It's kind of like a sculptor looking at a solid block of marble. How do they know what beautiful statue is hiding inside? Well, that's exactly the problem these diffusion models were designed to solve. And the whole concept really hangs on this beautifully simple two-part idea. First, you've got what's called the forward process. That's where we intentionally, step-by-step, destroy an image by adding a little bit of noise at a time. Then you have the reverse process, and this is where the learning happens. We train a neural network to get really, really good at undoing that damage, one tiny step at a time. It's all about learning how to retrace those steps, walking all the way back from total chaos to a crystal clear creation. Okay, so how on earth do you teach an AI to be this digital sculptor? Well, here's the key insight, and it's a bit counterintuitive. The model's real genius isn't in making pretty pictures from scratch. Nope. Its true genius is in becoming an absolute world-class expert on one thing and one thing only: noise. All right, now don't let all the scary-looking math on this slide fool you, because the idea behind it is brilliant in its simplicity. See, the original math for training these things was just crazy complex. But then, some researchers had a total breakthrough. They realized they could get the exact same result with a much, much simpler task. Instead of trying to predict a whole clean image, the model has just one job. Look at a noisy picture and predict the exact noise that was just added to it. That's it. That's the entire job. And if it can master that one little thing, well, that's where all the magic comes from. So the training basically boils down to this really simple repeating loop. Step 1, you grab an image from your training data, let's say a photo of a cat. Step 2, you pick a totally random point in the destruction process, a time step T. Step 3, you add just the right amount of noise for that specific time step to the cat picture. And then step 4, the most important one, you show that noisy cat to the AI and say, okay, what noise did I just add? The AI makes its best guess, we check how close it was to the real noise, and we nudge it to do better next time. And you just do that over and over and over again, literally millions of times, until it gets incredibly good at predicting that noise. Now, what's really happening under the hood, mathematically speaking, is something called the score function. And the best way to think about it is like a massive invisible map. It's a vector field. And no matter where a noisy image is on this map, the score function gives it an arrow, a direction, that points it back towards the highway of clean, realistic images. It's literally a GPS for getting out of the noise and back to reality. And folks, this is the big aha moment. This is the whole trick. It turns out that teaching the AI to predict the noise is just another way of teaching it to learn that giant GPS map. They are mathematically identical, two sides of the exact same coin. So by doing this simple task, predicting noise, the model implicitly learns the super complex map it needs to guide any random static back into a real, recognizable image. That's the genius of it. That's what makes this whole process actually work. Okay, so we've trained our model. Our digital sculptor is ready to go. It's a master at finding noise and getting rid of it. But wait a second, all it knows how to do is remove noise, right? How does that help us create something totally new from scratch? Great question. Let's see how that part works. To make a brand new image, we just run the whole process in reverse. We literally start with a canvas full of pure random TV static. Then, step by step, we show this static to our trained model and ask, okay, what's the noise in here? And we just subtract a tiny bit of what it predicts. We do it again and again and again, hundreds of times. And as we do, you can see a coherent picture slowly starting to emerge from the chaos until, boom, you have a fully formed image. Now there's a catch, right? There's always a catch. Taking all these tiny little refinement steps is what gives these models their incredible high-quality results. But taking 1,000 steps to generate one single image, yeah, that is painfully slow. So obviously the next big question for researchers was, can we please find a way to speed this up? And this slide shows the solution perfectly. The original method, called DDPM, was like taking a long, wandering, random walk through the woods to get to the final image. But a newer approach, called DDIM, is like hopping on a direct flight. It's a total game changer because it creates a predictable path, which means we can skip huge chunks of the process. We can go from 1,000 steps all the way down to maybe 50 or even just 20 and still get a fantastic result, a huge speed up. All right, so we get the process now, but what about the model itself? What does the actual brain that's doing all this work look like? Let's pop the hood and take a look inside the black box. The engine driving most of these systems is an architecture called a unit. You can see why it gets its name. It's shaped like the letter U. A noisy image goes in on the left, it gets squeezed down to understand the big picture, high-level concepts, and then it gets built back up on the right. But here's the really clever part. See those lines going across? They're called skip connections, and they're like little information highways, carrying all the tiny fine-grained details from the early stages straight over to the reconstruction phase. That's how it remembers things like the texture of a cat's fur or a tiny reflection in someone's eye. Now, the UNet is powerful, but it's got a couple of essential sidekicks. First, you've got time embeddings. This is basically just a little signal we pass to the network that says, hey, just so you know, this image is at step 900, so it's super noisy, or we're at step 10, it's almost clean. The network has to know this to make the right call. And second, you have self-attention. This is what lets the network look at the whole image at once and make sure all the parts make sense together. You know, so the dog's ears actually end up on the dog's head. Okay, this is great. Our model can now generate fantastic but totally random images of cats. But that's not really what we want, is it? We want to be the director. We want to be able to tell our digital sculpture, make me a cat wearing a top hat in the style of Van Gogh. This is all about control. And the secret sauce for that control is a brilliant little trick called classifier-free guidance, or CFG. It's kind of wild how it works. At every single step of generation, the model actually makes two predictions. First, it predicts the noise based on your text prompt, like a golden retriever. Then it does the exact same thing again, but this time it completely ignores your prompt. It then looks at the difference between those two predictions. That difference is the pure golden retriever direction, and then it just exaggerates that push, nudging the final result to be even more like what you asked for. That's what gives us such fine-tuned control. So we've gone pretty deep into the how this all works. Now let's zoom out and look at the so what. Because this isn't just some cool technical trick. This is a technology that's already having a massive impact on the real world, and it's forcing us to have some very, very important conversations.
So why did diffusion models take over the world of image generation? Well, simply put, compared to the older methods, they just worked better. The image quality was higher, they were more stable and easier to train, they just won. And things are still moving fast. The models you hear about today, like Stable Diffusion, use an even cleverer approach called latent diffusion. The idea there is, why work on the huge, high-resolution image itself? Instead, let's work on a much smaller, compressed version of it, like the idea of the image. It's way, way more efficient, and that's what makes these tools fast enough for all of us to use.
But, of course, with this kind of power comes, well, you know the line, a whole lot of responsibility. The same technology that lets us create incredible art can also be used to generate hyper-realistic disinformation and deepfakes. The models learn from the internet, biases and all, which means they can amplify those same societal biases right back at us. And then there are the huge unresolved questions around copyright and what it means when a model is trained on the work of millions of human artists. And so that's where we're left. We have successfully built a tool that can visualize nearly anything the human mind can describe. It's an unprecedented extension of our own creativity. But the biggest challenges ahead of us aren't technical anymore. They're human, they're ethical. We have to decide, what should we ask these powerful models to create? And maybe even more importantly, what should we ask them not to?